Hello everyone, welcome back to my channel, and today I am going to demonstrate linear algebraic equation using Gauss Elimination Method. So the learning outcome of this exercise, students should be able to utilize finite difference approximation to convert ordinary differential equation to algebraic equation. Secondly, students should be able to develop computer program to solve a set of linear equation system in chemical engineering. In this particular case, we will use Gauss Elimination Method. So the Gauss Elimination Method is generally consists of two steps, which is called forward elimination and back substitution. So if we have a system of A multiplied by X equal to B, where A is a matrix consists of coefficient and X is vector, and then B is the factor of constant. So we will convert this matrix A into a triangular matrix like this. So the upper triangular part will have new coefficient value, and then the lower diagonal part here will be equal to 0. And when you have upper triangular matrix like this, you can easily compute what is the value of x3, x2, x1 for this case of 3 by 3 matrix. So we will call this step as a back substitution method. So the detail of this theory can be read in the textbook of numerical methods for engineers. Alright, in this exercise we are going to solve concentration distribution in a solid cylindrical catalyst. So if you have a fixed bed reactor, you will have a bed of catalyst, and then if you look at the catalyst, you will have concentration profile if internal mass transfer is important compared to the reaction rate. So this problem is taken from our textbook here, and the plan is we are going to solve the differential equations that we obtain using linear algebraic system. So the solution that we expect is something like this. So here is the narration of the problem. We would like to study the diffusion and reaction in a solid porous catalyst. The catalyst has a cylindrical shape with radius of r, and we have reaction which follows first order reaction rate, and then we have also internal diffusion. So boundary condition here at r equal to capital R, or at the surface of catalyst, the concentration of A is assumed to be the same as the concentration of A in the bulk liquid. And by solving mass balance and taking volume element, we will end up with this differential equation, or this is called as a Bessel equation. This is classic equation for cylindrical system. And in order to solve this equation, we need to boundary condition at r equal to 0. We can set that the dCA over dr is equal to 0, and this is Neumann boundary condition. And then BC at r equal to r at the catalyst surface, the concentration is equal to the concentration of A in the fluid, or this is Dirichlet type boundary condition. And for your calculation, we already provide what is dE, K, R, and CAF, and we're supposed to plot the distribution of concentration as a function of R, and then we also need to calculate the effectiveness factor as follow. Alright, in order to solve this equation, the differential equation, we will convert this differential equation to a linear algebraic system. How to do this? We will use finite difference approximation. So approximation for first derivative, here we have forward, backward, and center approach. And to get better accuracy, we will use second order error here. And similarly, for second order derivative, we can approximate this value using this formula. And this is basically center approach. And if we divide the catalyst radius from 0 to r, we divide it into 11 points here. So then we can make a discretization according to FDA method. At I equal to 0, it is mentioned that the dCA over dr is equal to 0. So then if you look at I equal to 0 here, it doesn't have any any point in its left. So we can calculate the dCA over dr at I equal to 0 based on the value of at 1 and at 2. By using this forward approach, using second order error, we can obtain this formula: minus 3 times Ca0 plus 4 Ca1 minus Ca2 equal to 0. And then at I equal to R, it is mentioned that the concentration here is assumed to be the same as in the bulk liquid, or sorry, in the bulk fluid, and we call it as CAF. And then for I up to 9 here, we have this differential equation, and the thing is, here we will convert this to algebraic equation using FDA. So the d2Ca over dr square here, we can use this formula, and for example, for I equal to 1, we will obtain this blue equation. And similarly, if you convert this using FDA, 1 over R multiplied by dCA over dr using center approach, that's equal to this one for I equal to 1. I equal to 1 here, because the good thing when you are in the interior point at I equal to 1, for instance here you have the value at the left and value at the right, so you can use center. And if we continue here, so after we convert dCA over dr becomes this one, the red one, so we can also convert minus k over dE multiplied by Ca at I. In this case is 1. So in general formula at I between 1 to 9, it will follow this general formula. Okay, so if we look at closely, this is basically a linear algebraic system. So after we convert the ODE to linear algebraic equation, you will have this matrix A 0.0 up to nr minus 1. Sorry, I have to edit this. This should be nr minus 1. All right, so you will have 11 points, 11 by 11 here if nr is equal to 11, and then you will have vector which has the size of 11 by 1. Similarly here b is 11.1, and the value of Ca at various position as a function of radial position can be obtained using Gauss elimination technique that consists of 2 steps: forward elimination and back substitution. So the program structure for Gauss elimination, we will have main program, we will provide all the data that we have here, and then we will do forward elimination and then back substitution to get the result, something like this. Alright, now let's move to Spyder. We can have Spyder environment here. So we can start with importing a library as usual. We can say import numpy snp and then import matplotlib.pyplot as plt. Alright, now as usual we need to provide data, and then we don't have really subroutine now. I would say this is forward elimination, and then we'll have back substitution. Alright, this is in general. To speed up my tutorial today, data, I have written this in a notepad. I can just copy that information here. Alright, so this is the data that we have. We have the effective diffusivity K, R, CF, and R. In this case, we decide to have 11 points, and dr, that's equal to R divided by nr minus 1. And A, here this is pre-allocation for matrix A. Matrix A. So if you check nr is 11 here, so this is 11 by 11. But now the element here, if you run this code, if you check variable explorer, so the A here is basically all 0, but the size is already correct. This is 11 by 11. And similarly, B is basically 0. And now we start constructing a matrix. If you want to check R, we can also do that. And this is the spacing for R, the radial position. Okay, before we do forward elimination, we need to construct matrix A according to FDA of matrix A according to FDA. And for I equal to 0, we know that A 0.0, that's equal to -3. This is 4, and then A 0.2, that's equal to 1 or -1, and then A, that's nr minus 1 comma nr minus 1, we will have 1. And similarly B, like nr minus 1, that would be equal to CAF. Oops, CAF. Alright, now we can check how our matrix looks like. As expected here, we have -3, 4, 1, -1 here, and then 1 here for the catalyst surface position. And then for B, here is the value. Everything is 0 except the last position where the concentration equal to CAF. So the constant is CAF basically. Alright, now let's fill the matrix A using for loop. So now for I, so again, I remind you that for this position from 1 to 9, from 1 to 9, it follows this formula, okay? So now for I in range, this is basically from 1 to 9. 9, we types n here, or nr minus 1, that's 10. This is really to force the index to work from 1 to 9. Okay, now we can start filling the matrix A. I comma I minus 1 equal to 1 over the R square minus 1 over 2 multiply dr times Ri. Okay, so that's for I minus 1. And then the diagonal element we can just copy first to save the writing time. And then for I plus 1, it is quite similar with minus 1. The thing is, we only need to change the sign as a plus sign. And then for a diagonal element, it follows this minus 2 over the R square. Oops. I have to put double dot there. Minus K over DE. So now, by doing this, we can have a new matrix of A. So it's expected here. Oops, I think there's a problem with I comma I. Check again. Alright, now it is correct. So this is, we call it matrix three diagonal matrix of A, where we have the 3 elements in the diagonal. Alright, now let's continue our exercise by doing forward elimination. So I'm not going to discuss detail about the theory of Gauss elimination. You can check in the textbook, but I just focus on doing this forward elimination, and we do as follow. So we need to define the small a and then n as the length of b. Okay, I need to provide more space there. And for I in range 0 to n, and we put like this. And then for j in range, this is I plus 1 up to n. And then we can have something called factor. This is to normalize the coefficient in the A matrix. So that's basically a j comma I divided by a I comma I. And then the a at row j equal to a row j, and then minus f multiplied by a I, so the row I. So this will obtain new coefficient for row j. And similarly, we need to correct the value of constant there. B index j equal to b index j minus f b index I. So here it is now, our new matrix A, or small case a. So this is called triangular matrix. Well, you will see here that there's some value here. It should be 0 basically, but if you open this one, this is very small number. This is e minus 16, e minus 15. So this value is very close to 0. Okay, so we can assume that this value is equal to 0. Why we have small trace here? Because we have irrational number here, 3 3 3 3 3. So that makes some small residue in the calculation. So it doesn't matter. So now we will do back substitution, and let's say the factor of concentration is, we call this as x, and that's np.copy np.zeros. This is for pre-allocation again. This is the length is b. All right, and then we have to define what is called sigma. So that's np.copy x. And back substitution a little bit more tricky here, the indexing, because we start from behind. So let's define for k in range, because it starts from behind, minus 1 should go downward and then up to 0. And to make sure that 0 is included, we put up to minus 1. So it means that we will start from n minus 1 is 10, 9, 8 up until 0. So that's how k will evolve. And then let's define the second index for L here in range of k plus 1 comma n. Oh, we need to put double dot there. And then let's define what is sigma. Sigma L, that's equal to a indexing k comma L multiplied by x L. So this is basically like matrix multiplication. And then the new x k is equal to, this is back substitution, bk minus the sum of sig and then divided by the diagonal element of A, K, comma, K. Alright, so that's the back substitution method. We check again, K, comma, L, X, comma, L. If you run here, the X value here, it should give the concentration of reactant in every position, in radial position. So from 0.001 up to 0.005. Seems like it's correct now. Okay, so basically that's all. And now we need to do plotting. To speed up my tutorial, plotting is the same like in previous exercise, so I'm not gonna focus in that one. I can copy from my notepad code the thing that I have prepared earlier. So if you have the xk and then you want to plot r, x, you can print that value again. So here it is, the table showing the position in radial position and then the concentration. And here's the result of our table. Very nice. So as expected here, in the catalyst surface, the concentration is the highest at 5 E minus 4 gram mole per cubic centimeter, and then it will drop and drop to the up to the center of the catalyst. Okay, and in the second part of our exercise, we are supposed to calculate the effectiveness factor. Effectiveness factor is basically a ratio between mass transfer and reaction rate. So here's the formula. So we will use Simpson method because we already have the R as the radial position and Ca, what is the concentration of A in every radial positions. Oops. So I mean this one. Okay, let's go back to Spyder, and to speed up my tutorial again, I just copy from previous exercise because my focus in today's exercise is not about Simpson. For Simpson code, you can check previous tutorial, and we can say the position of integration, it starts from 0 up to R, and Ca is np copy x, so basically the same as x. And then you need to define the subroutine here for your integrations. In this case is R multiplied by Ca, and then you do Simpson, and then the integration is as mentioned in the problem, 2 over R square over CAF multiplied by dr over 3 sum fsim. So this is the integration part, and when you run this code, you will get the effectiveness factor as high as 56.46%. So as you see here, so we have the concentration of A as a function of radial position here. This is the value if you are interested to know. And the code, it consists of data and then construction of matrix A, construction of matrix A, and then forward elimination and back substitution, because forward elimination, back substitution, and also the use of FDA here, these are the focus of today's exercise. So, and when you do that, you will obtain the concentration for every radial position. So thank you for watching. Hope you find it useful for your study, and good luck. Thank you. Bye bye.